Hello everyone. Hello everybody. Good morning, good afternoon. I don't know where you are. For the people on the television, not on television, on the Zoom. I have the honor and the privilege to actually introduce the demo day today. I will first go through a couple of slides to introduce what GCCA is and put that in the context of our journey. And then we will go through all the demo startup. There are four, and explain some news from the previous Open Challenge. So first, a short word on GCCA. So GCCA is the Global Cement and Concrete Association, as you know. We are regrouping basically the leaders of the industry. We like to say that we are a CEO-led organization. That means basically that the companies that are members are really bringing the leadership into the association. We have different type of companies. We have really majors companies from all over the world, majors from Africa, majors from India, from Latin America, from Europe, of course, from USA. And we also have some mid-size and some small companies. So that's really a big diversity. And I have to say that we are a fairly attractive association. I mean, 10 new members over the last 12 months. And that's thanks to basically the agenda that we have. And this reflecting the commitment of our industry to sustainability in general and to the net zero journey. In particular. We are also working on cooperating. We are partnering with the National Cement Association across the world, and we are in a privileged communication with all the national and regional cement and concrete associations. So that's part of our representation. We like to say that we are covering 80% of the world outside China. However, in the last few months, we have actually China Cement Association that join us. So today we are actually 80% probably of the world if we consider that CCA is valid for all China. Now, let me move forward. The DNA of the company, as I said, is 5 strategic pillars. At the center of our vision is the net zero strategy. This is really the challenge of the industry, of the sector over the next years. We know that. We know the CO2 footprint. We have to say that the CO2 footprint of our product comes also because it's an essential product, because it's a very popular product. It's a popular product because it's available, and because it brings essential things to the modern world. And we like to say that we are the backbone of the modern world, right? And that's associated. Concrete is associated to modernization and to higher economic, socio-economic living, and that makes it difficult to decarbonize because it's a global product. So when we think startup, when we think technology, we have to think scalability before and everything due to that geographic diversity. We also have 3 essential missions. The promotion of concrete. I mean, yes, we say, voila, we have an essential product. We explain what we do in terms of decarbonization, and we say, look, concrete is a nice product actually in many extents. We have sustainability also. We work on all aspects of sustainability, nature, water, everything that concerns exchanging best practices, making sure that members get the information and can progress on the sustainability journey. And we have innovation. Now that's what we are doing here. Innovation is really, I like to say GCCA is an innovation organization. We are on that point very modern or very peculiar from a trade association, if you want. And that's about 1/3 of our activity. So 1/3 of the budget of GCCA is allocated to research. Is allocated to the research network that we have. I will come back to that. And that's really a big thing for us. So why do we do that? So I mean, how did this is all happen? It's basically this net zero roadmap. So we have this commitment, collective commitment to go net zero by 2050. And you see, we have identified 7 levers to advance and to progress on the net zero journey. And the innovation is basically there to accompany and to work on these 7 levels and say, okay, how can innovation can help us actually work, accelerate, progress, develop the discussion, facilitate the development on the journey. And that's basically what we are doing here. Innovation will help us. I mean, what we like to say is that our roadmap is feasible with the technologies of today. I mean, in principle, we can achieve today with what we have, but innovation will help us to actually accelerate, facilitate, and probably make the transition less expensive also. And that's what we aim to have with innovation. So how do we work with innovation? We have 3 platforms. The first platform is this research network. That's the pot where the money is going. It's really research in cooperation with academics. We have partnership with 45 top-class academics around the world, covering from Africa, again India, all Asia, Americas, of course, etc. We have 80 PhDs working on different topics. We are making tremendous progress, to be honest. I mean, we are very proud. I'm very proud of this research network. And we have about 450 scientific community that is at reach, available for discussion, sparring, etc. And that's important also in the context of the next discussion, which is the Open Challenge. So that's where we are today, this startup accelerator, where we basically believe that startups can help us to actually accelerate. Edelio will come back on that, and he will explain in more details. We have also launched the third platform, which is the Entrepreneur Network. On there, it's more about getting, a collaboration with technologies that are not necessarily the center of the Open Challenge, but that are also needed potentially, or that can help us also advance. On there, we want to basically present, inform, discuss with the startups all over. So that's for the introduction. I would like to call on stage my colleague Edelio Bermejo. Please, thank you very much.
Thank you. Thank you very much, Thomas. So thanks a lot, and good afternoon to everyone. So I will be presenting this demo day, but first of all, I would like to say a few words about this Open Challenge. So as Thomas said, we need innovations. We need innovations in the entire value chain. So from architects, engineers, to propose and to develop and to prescribe the low carbon solutions, till the government that have to incentivize the low carbon technology. So materials and technologies have to evolve in order to reach the net zero. And in between, we will have the developers promoting these low carbon buildings, and we will have as well the public authorities imposing green procurement. But in this entire value chain, we absolutely need to contribute to the net zero journey. One way to do it is to do the academic research. Another way to do it, and that will be the focus today, that will be the partnerships with startups. Startups are playing already a key role in innovating, but we need to help them. We need to help them to make them fly and to have the solutions developed at scale. If they are still too niche, that will not solve the problem. So we need to create that scalability capabilities. And for this, we launch this industry-led accelerator. I insist a lot on the industry-led. That means that we are defining the challenges. We are defining the needs. This is not just scouting companies, startups, for financial speculation. No, this is because they are answering to strategic needs. There is a strategic rationale behind. So that's why we launch it. And the objective is to fine-tune these technologies. Again, I repeat, based on what we need, what the industry needs. And obviously, the objective is to accelerate these technologies. So we're starting from low TRL companies to medium TRL companies, and then the objective is to provide them the ecosystem to scale up. And what does it mean? What are the benefits for these startups? That they can have access to the mentors, to the engineers, to the experts that this industry, that the GCCA is gathering. So that's a tremendous value, because they will have this stamp from the GCCA members that the technology has been selected by GCCA, and this is a relevant one. Obviously, we're providing facilities as well, the labs, the plants. Let's imagine for a startup getting access to a ready-mix batching plant in order to test their low carbon materials. That's fantastic. This is a fantastic opportunity for them to scale up. And again, scalability is the key word for these startups. As I said, 40 members today helping the startups, mentoring the startups, and even improving the business model of the startups, which is or can be as important as just developing the material. Obviously, supporting, we need to make them fly. So we're supporting that from the pilot phase, from the ID generation, or fine-tuning the ID generation to the pilot phase, and then to the investment through a unique facility. This is the process. First, we define an objective. Second, we scout all the different startups that did apply, answering that challenge. We're not just scouting startups in the field of low carbon technologies. They need to answer to a specific topic. Then we made the pre-selection and the selection and then the onboarding. And during 6 months, the GCCA members are working with the startups, are developing, assessing these technologies, and even testing. And the startups on their own are testing as well what could be the potential of success of their solutions, their technology, or their materials with regards to the challenges that have been defined. And then we have the demo day, and this is today. So today we will be presenting some startups that have been selected, that we have been working with for the last 6 months, and the objectives for you is to assess if these startups are relevant for your challenges. And then this is just a matchmaking, so they will be presenting. If you like it, you discuss directly with these startups. So the challenge 2023 was very much dedicated to low carbon materials. The previous one, 2022, was about CCUS technology. This time we decided that it should be more on the material side. And then we went through this challenge dedicated to new materials ingredient for low carbon concrete. 70 startups were sourced, 15 have been pitching. And then we selected some of them, we created some consortium, and 4 made it a consortium. And these consortiums were assessed, some companies were participating to this consortium, but the very, very important point is that 65 experts have been assessing. So the ones that you will be discovering now are the ones that we strongly believe are the best one according to that challenge. So Queen's Carbon, EnviCore, Chement, and Neocrete will be presenting today their technology. These are the mentors for this challenge, for the challenge of the Open Challenge 2023 dedicated to low carbon materials. These companies have been assessing that, and what I suggest now is that we go through the presentation of these startups. In order to be fair with all of them, the startups will have 12 minutes and not more, I insist, including the Q&A. So you manage the time the way you want, but at 12 minutes, we stop and we need to be fair for the next one, etc. etc. So we will be very strict, and Devika, our legal and timekeeper, will be very strict on this one. Okay? So what I suggest is that we start with EnviCore. You tell me, and then the clock is starting.
So I can start. Yeah.
Let's go.
Thanks a lot, everyone, for joining me and others for this great event today. My name is Shamim, and I'm the CEO and co-founder of EnviCore, and we are a Calgary, Canada-based company. And our motto is closing the loop. We are supporting the construction, or in specific, cement and concrete producer in being, again, like pushing the decarbonization limit, specifically by transforming different type of mineral feedstocks into SEMs. And our idea is to, again, go as high as replacement as possible. We're starting with 20% cement replacement, and definitely SEM1 cement replacement in the mortar mix, and assessing the performance of the material before and after the performance or after treatment with our technology. Now, how do we do it? So we have developed a patent-pending process that basically takes any type of mineral feedstocks, again, depending on the favorable mineralogy, it would be ideal. But then we have tested recycled concrete fines, aggregates, metal tailings, or basically mining tailings coming from copper, nickel, cobalt, even gold and aluminum mining operations. And then any other type of metal slags or metallurgical slags, such as steel slag, electric arc furnace, basic oxygen furnace, or even copper slag as well, coming from a completely different operations. And then slag, ash-based material, ponded ash, bottom ash, and other type of natural materials, such as clays and natural pozzolans as well. And our process is divided in 3 interesting steps. our first step is definitely mixing or homogenizing our proprietary chemicals with the mineral stream in a very desired fraction or ratios. Now we mix it in a ball mill or basically another type of homogenization like process to achieve a partial activation of these minerals with the chemicals that we add. Now that material is then transformed or transported to another step, which is tempering stage, where we get the complete activation of material, basically going from inert or low reactive material to a high reactive material. And finally, to comply with the ASTM, CSA, and all the other standards from a fineness perspective, we are going with the final SEM grinding, which can easily be associated or combined with the clinker grinding as a co-grinding process. And the overall process, it's called Chemical Assisted Tempering Process, or in short form, CAT. Now, we developed this technology back in 2022 or early 2022, where we were just processing small batches of sample in a batch mode, like just 200 grams in a roller jar mill of 5-liter capacity. We have static furnaces that can go up to 2 kilograms, but again, in a batch phase process. And finally, for the finished mill, we were doing pretty much the same capacity. But then we decided to scale up the process internally, just in our own warehouse. We were able to develop a semi-continuous operation that can take up to 8 kilograms of material per hour basis. And we have a dynamic furnace that can actually be continuously processing the material to achieve the activation. And that can do up to 5 kilograms an hour. And finally, again, the same capacity mill for our finish mill, again, if we are not doing any co-grinding. Going into the KPI and benefits of our technology, like till now, we have tested close to 38 different streams just to understand the viability and versatility of our technology. What sort of mineral stream doesn't work for our process? What sort of mineral streams are ideal for our process? And this exercise has helped us to nailing those specific parameters that we need in our material to succeed in producing a high reactive SEM. Our next scale up that we are working actively right now, that's going to produce it's planned actually 600 times bigger than what we are currently doing. And we'll be deploying with our collaborator in the cement industry. Now, from a footprint perspective, as since we know it's very important, 1 ton of SEM production in current scenario emits close to 90 kilograms, and we are trying actively to reduce this number as well. Our idea, again, is to maximize the replacement level. So we have done independent and third-party testing as well on certain material that can go up to 30% cement replacement in a mortar and concrete mix. The additional benefit, what we are providing along with increased performance, is the reduced water demand, which is quite beneficial for concrete and cement producers both. So we are trying to come up with a holistic solution to provide this decarbonization effort at the same time be on good on the durability and performance side as well. Again, I'm going to emphasize on the scalability of our process because now the plant capacity for the pilot is going to be 600 times bigger. Our commercial scale would be at least 500,000 tons, but it's very specific to geography and also material availability and demand of SEM if we are working independently or with a cement company. We have close to 5 patents right now, all PCT applications to cover the breadth of our process, not just the process parameters, but the family of chemicals, the proprietary chemicals that we add in our process. Our technology covers approximately 4 UN Sustainable Development Goals, going all the way from sustainable city development, infrastructure development, to climate change mitigation. And right now, we are working actively with 16 global players, not just cement industry, but mining industry has been stepping up specifically to target their waste production, especially the tailings issue. And I want to thank incredibly to Innovandi Open Challenge and GCCA for providing this amazing platform for startups like us, where we get to showcase our process, the benefits, and subsequent results. And again, kudos to all the cement companies who are trying really hard on achieving the net zero goal by 2040, 2030, and so on and so forth. But the objective of our consortium was pretty straightforward. We received 12 different mineral streams, and we were supposed to transform them from either being low reactive or inert to a high reactive SEM. We were supposed to do ASTM C618, which is 20% cement replacement in the mortar mix. And basically, just send the material back to either third party, or technically third party, and clients as well for result validation and corroboration. Now, based on the 12 samples, we categorize these different samples in, again, like different categories. The first category is recycled concrete fines. And there are a couple of parameters that we're going to just talk about. Strength activity index, pretty common in the cement industry, is basically your strength, compressive strength of your material. That means your blend of 80% cement, 20% SEM, divided by your 100% controlled cement. The solid blue bar shows the processed material, and the checkered one shows the as-is, but milled to the same extent, because milling does impart amorphization in the material. It's been reported too many times in the literature. But in this case, we have shown that it went from, at day 7, 92% SAI, again, relative to controlled cement, to 95%, again, showcasing that it's considerably better than the as-is material, even after milling. Other category that we got was clays and natural pozzolan. So we got low reactive clays alite-based, low reactive clays montmorillite, then black shale and diatomite. And then again, in same cases, day 7 to day 28, we are constantly seeing better performance in all of these materials. In certain cases, it's even surpassing the cement 100% control strength. The third category, ash-based materials. So we have ponded ash, bottom ash, and bagasse ash. Again, similar trend. We're getting improved performance at day 7, and even further improved performance at day 28. So the trend is pretty clear. We're looking at improved performance at day 7, and the reactivity is either maintained or increased at day 28. And the last category that we got was tailings and slag. So we got metal tailings, steel slag, which is slow-cooled slag, coming from our electric arc furnace, and then iron ore slime. And again, we are still generating some of the samples data for 28 days, but the trend is very clear. We are looking at improved performance at day 7 and day 28 as well. So what's next for EnviCore? We are trying actively to complete the GCCA project by, first of all, fulfilling our internal validation, and then sending the samples back for third-party testing and client validation. Our engineering team is actively working on designing the pilot that we will deploy in Q1 of 2025. That's the anticipated timeline. But right now, the idea is to source and talk to all the vendors possible to achieve a more detailed quotes on our CapEx and OpEx for the plant. Again, upon successful completion of pilot scale, we'll be going for a commercial deployment of 200,000 tons per year, again, depending on the location, availability, and at the same time, the demand, the local demand of these type of material. Now, we know that we are working with active players, global players, and we really want to bring our technology to the market. So we are looking forward to collaboration, either in the form of joint venture or potentially licensing the technology so that we can bring our technology to the market. So with that, I would like to conclude my presentation and open the floor for any questions. Thanks.
So we have 2-3 minutes for questions, and I think that there is one question online.
Oh,
yes, yeah, it's working. So I have a question from Mir Ali, who is asking, can the SCM from EnviCore only replace cement in concrete, or will also be able to replace clinker in cement?
We can do both, actually. The whole idea of using the conventional equipment to mimic the whole clinker replacement process as well. Because if we have the final step of milling, if we just remove it and put our SCM along with the clinker by replacing it, some portion of it, depending on what's the performance requirement, we can definitely achieve clinker replacement along with cement replacement down the line. Separately, though. Yeah.
Tempering process?
So in this case, we have maxed out the temperature range to 700 degrees Celsius because we don't want to, 700, yeah, we don't want to go beyond that. But for certain material, we don't want to even go up to that temperature. So our case is 500 to 700 max, but it's highly dependent on what type of material you're dealing with. In certain cases, like if you have clays, especially kaolintic one, 500 is more than sufficient. But then if you're doing tailings-based material, which is highly inert, you're going to go up to 700. But that's our limit.
Hello. So you are going to use some proprietary chemicals.
Yeah.
What about the cost viability? We are considering there will be 20% cement replacement, but at what cost?
Oh, the cost.
Do you have some idea?
Yeah, no, absolutely. Great question. So from a cost perspective, it's very geography specific answers. Like in North America, we have a different standard. In Asian countries, a different standard. So to give you a specific answer, it would be very difficult because we have to do a case study based on where exactly we are planning to operate. But in a nutshell, these chemicals that we are calling proprietary chemicals, these are commodity chemicals. So these are available pretty much everywhere. And it's not expensive. These are not specialty chemical to start with, so that you don't have the lead time to procure it and use it in your process. I hope it answers the question.
Yes, but the 12 minutes are over. I'm sorry for that. So, but the point for the ones that are in the room, no problem. It will stay with us. So thank you very much. And again,
Thank you.
next one, Queen's Carbon, and you tell us as soon as you're ready.
Thank you.
Yes, definitely ready. Thank you very much for everybody for being here. Of course, there's a lot of people online that were not here. So hello, if my kids are watching, it's time to be sleeping because it's 12 hours ahead. We're Queen's Carbon. I'm the CEO and co-founder of Queen's Carbon. My co-founder Dave is in the audience. Find us after. We'll answer all the questions. We are a material science focused company. The core of our company and technology is material science through and through. We know how to solve the chemistry problem. We know how to solve the CO2 problem in cement. But we need the industry's help to scale the process and to support us as we scale on our journey. Of course, everybody knows this. The entire conference is associated with the CO2 footprint. We hope to, of course, solve that challenge. And really, the core of our technology is this reactor technology. We can use the same exact raw material feedstocks, limestone, sand, the exact same raw meal that's today used in the cement industry. We put that raw meal into our reactor, and we've discovered a unique way, a proprietary way to use water and a particular steam pressure inside of our reactor to lower the temperature of the chemical transformation. So we're taking limestone and sand, we're putting it into our reactor, and we're making various calcium silicates. Those calcium silicates are collected at the outputs, and we call them ACMs and SCMs. And we can tune their performance based on the degree of pozzolicity and the degree of hydraulic activity. We have a co-product on the end side, and it says optional, and I'll describe what I mean in a second. Our co-product is high purity CO2. What you don't see on the screen, you don't see any CO2 purification steps. You don't see any chemical complexity. You don't see any acids, bases being added to process things at low temperature. I missed that point earlier. 500 degrees is the operational temperature of our reactor. And so that water pressure, the proprietary water pressure that we've discovered for this process allows us to make these materials very, very low temperature. The CO2 stream is optional. What do I mean by that? If there is no CO2 off-taker at your site, we can mineralize back into our product and make a very pozzolanic system. If there is a CO2 off-taker, wonderful. Make a B-light-rich cement, and we can do that with our process. You could think of us as the Instant Pot of cement manufacturing. Just like legacy cooking was revolutionized by the Instant Pot, many of you may have it at home, the legacy cement process will be revolutionized by our Q reactor process. The same thing, you're adding your chicken, you're adding a little bit of water, and the cooking process begins. And I'll get ahead of all the questions right away. This is not going to be a batch process at scale. We're focused on continuous, and we're focused on scaling up this technology. Your plant today is located at a quarry. We want to be located at the exact same quarry. We want to take that limestone, we want to take that sand, mix it at the exact same crushing and grinding step, and not disrupt the calciner. The calciner, the kiln process should stay the same because the forklift upgrade to that process today in 2025, 2030, 2035 is a big ask for the industry, and we recognize that. What we're saying is give us 20, 30, 40, up to 50% of the material stream. Give it to us in our Q reactor. We will process it. We will either make a carbon neutral SCM or a high purity co-product CO2 and a hydraulic cement material. Take our material, blend it back into your product with zero change for you on your plant. You did not disrupt your kiln, and your customer never saw a difference. So what did we actually do here? We vertically integrated the SCM supply chain into your cement supply chain. No need to rely on logistics, no need to rely on ash, no need to rely on any SCM that you would otherwise do it. Now you control that world. And where do we come in? We make the technology. We are not cement plant builders, we are not cement plant operators. We make the technology, we give you the technology, and you run your plant and enable your decarbonization footprint. The key is, and why we're here and why we're excited to be here with the GCCA, is we want to be symbiotic with all the legacy operations. We want to make decarbonization as simple and cheap as possible. We started our journey at Rutgers University. Some of you may know Professor Richard Ryman, one of the originating Clean Tech 1.0 pioneers. We licensed the technology and we won the Breakthrough Energy Fellowship that funded our start. And for the past 2 years, we've been developing our prototype. And I'm happy to say we're getting very close to securing funding for our continuous and semi-continuous and continuous operation to bring this technology to scale. We understand how the chemistry works. We also believe we know how to scale this process, but we need your help to support the deploy. So we're always looking for partnerships on this continuous pilot and full-scale demonstration plant, and we need your support to test the product and validate the product. It's not just me. Dave Gershalowitz is in the audience. He's the business co-founder. I'm the technical co-founder. But we're here because we've hired an expert material scientist, an expert technical manager that can lead our R&D operations back in New Jersey while we're on the road. And of course, you could look at our sponsors. You could look at who we're affiliated with. We're looking to de-risk this technology with venture funding, with industry support, and of course, non-dilutive grant. And that Scale Up 2023 finalist really refers to that, if people are familiar with the Department of Energy grant. Thank you, right? We're very happy to be part of this big consortium that, we didn't do the exact math of how much % of cement this covers globally, but we're very satisfied with the members that joined our team. Specifically why? We need to hear your input. We need to help validate our materials and validate our products and processes. We can say all day that we have the best material, but without your support, it means nothing. So what have we done with the consortium today? We've received diverse raw meals from your plants. We've processed it in our reactor, and we're on ongoing testing, and we'll send samples out to the consortium members for third-party and external validation. A few of the performance data can be seen here. ACM refers to the hydraulic material. SCM refers to the more pozzolanic material. In all cases, the performance is very satisfactory, and in most cases exceeding that what you see of fly ash. So we have good early strengths, and we approach 100% for every single mixture. This is a 30% PLC replacement. So if you add the limestone that was already in PLC, we're already reaching about 40% in terms of clinker replacement. In the lab, we've done up to 40% replacement without including the PLC. We believe we can go much higher. I mentioned the ACM product is a hydraulic product. Our hope is longer term, 100% replacement. When the industry is ready to retire the kiln, put our Q reactor in place. Until then, put it in parallel and don't disrupt your process. So the header of this slide is really what this is about. We want to have no compromises on the journey to decarbonization. Today, we're excited to say we could do 20 to 50% less clinker, which means 20 to 50% less CO2, and we want no compromise. We don't want to blow up the energy stack. We don't want to have 6 gigajoules or 8 gigajoules per ton of energy. We believe our process is 2 to 3 gigajoules per ton, and that's due to that low temperature aspect. And of course, the cost will follow. There's a lot of ambiguity of how the process will scale, and that's what we're funding now to de-risk. But the actual energetics of the process, we have a good lever of predictability there, and we're excited to say that we're cost competitive, probably with cement and most SCMs in the market. With that, thank you very much. You can find us at our booth, and happy to take any questions. Thank you.
So we have more than 4 minutes for Q&A. So we have some questions online. So Claude?
Yeah, I have two questions. One from Christian Bogetou. Will cement players license your tech? Cement players typically like to own the tech and not license it, right? Maybe more a question to cement, but I think you know the answer because we have rules in our challenge.
Sure. So the main objective of our company and our mission is to do what the cement industry wants us to do. So and that's how we're framing our business model, which means we want to build the technology and give that technology to the cement plant operator. There could be a business model in which case there's a revenue share, but we're not ready to discuss the nuance of that just now. Yeah.
And then the next one is based on your testing, what kind of cement strengths have you seen by utilizing the technology?
Cement strengths?
Cement strengths, yes.
At 100% replacement, or I guess SCM replacement?
They don't say in the question.
That was the previous slide where we really showed the strength activity index, which refers to the PLC control. So we're basically matching. After 28 days, you don't see a difference. Beyond 20 days, it gets even better than PLC standalone. So the idea is, again, the header here says it. You don't want compromise. You don't want cost compromise. You don't want energy compromise, and you don't want performance compromise.
We have questions in the room. So first one, ladies first, sorry, and she was first, and then here and there.
Okay, hello. I would like to learn about how you manage the homogenization inside the reactor. the material because you are mixing limestone and sand? And my second question about the electrical consumption per, cementitious material. Thank you.
Sure, thank you. First, on the homogenization question, our intent is to use the raw meal. So we don't want to do any pre-processing of the material. Maybe we would change the amount of limestone to drop the calcium to silicon ratio, but that's it. So on the feedstock input mode, and I think you're asking about what actually happens inside the reactor, but on the feedstock input mode, the homogenization is what the raw meal, what comes out of the vertical roller mill is what we are putting inside the reactor. Inside the reactor, no homogenization is necessary. You want the atmosphere to turn over, you want the material to be agitated, but that's it. So the physical mixedness of the material that you're putting inside the reactor is good enough from the VRM output. So you don't need any complex homogenization inside. On the electrical conditions, we really do our calculations in terms of gigajoules. So 2 to 3 gigajoules per ton is the strike zone, which is lower than what the energy is on average to produce clinker. Yeah.
Question number 2.
I'll sneak in 2 questions. One is that assuming that your statement about carbon neutrality is correct, am I right to assume that the reactor will run on electricity and not on fossil fuels? And then the second question is that does the hydrothermal process result in a damp product that would need further drying?
It's a very good question. And I'll answer the second question first, because maybe that's more relevant. I don't include a drying step because there is no drying step. The products come in dry and they leave dry. We don't believe in any chemical complexity or chemical engineering complexity. We believe adding any step will actually destroy most next-gen emerging technologies because now the chemical complexity of your plant is just too high for a cement industry. This is not the aluminum industry, right? This is the cement industry. So you really have to think in terms of simplicity. And the first question, remind again? Right, so it's energy source agnostic. Most of the energy goes into heating the water. So what your boiler looks like can be fired by fossil fuel or electric or geothermal or waste, and we could do a mixture of those as well. If you look at the carbon footprint analysis at a 30% replacement, it's very, very little dent if you use natural gas. So initially, when your plant is not fitted with the right amount of electricity, you may want to use natural gas as a placeholder. Longer term, decarbonize, right?
And the very last question.
Yeah, so part of the question he asked as well, so mine is similar questions. I presume that the high pressure applications are converting this the reactions, right, rather than the traditional kiln process. Mm-hmm. So the CO2 reduction comes from mainly the fuel, not the process, right? That's the way you look at it?
Yeah, generally that's the correct way to look at it. There's fuel heating, right, and then there's the limestone decomposition. In the SCM, which is carbon neutral, where we're absorbing all of the CO2 back into our system, all of the limestone emissions are solved. When we can't solve those emissions, if you're making a hydraulic cement, if you wanted to make a belite rich mix, the CO2 co-product is now pure. So you didn't charge, like in the CCUS retrofit case, where the cost of cement doubles, you keep the cost of the cement the same while providing this CO2 to your off-taker. So when you're thinking about where the CO2 goes to utilizer or pipeline, the cost there is now reasonable to that utilizer.
Thank you very much. Thank you, Queen's Carbon.
Thank you.
So we move now to Chement.
Right. Thank you very much. So yeah, my name is Greg Houchins. I'm the CEO of Chement. And so just like Queen's Carbon has used pressure to change the thermodynamics of cement production, we're using electrochemistry to make a complete replacement to conventional clinker. And so, the idea of this is to think about other large-scale electrochemical processes and how can we fit an electrochemical process to make a hydraulically active calcium silicate into that. And so we've come up with a process that's more energy efficient. So if you're using grid electricity, you could still decarbonize your energy compared to a kiln today. And of course, if that's green electricity, you can get that down to 0. The output of our process is a lower calcium content calcium silicate. So even if we're using limestone, we're using less limestone, so we can decarbonize the amount of direct emissions that come from decomposing limestone. And then the last part is if we want to go from a massive reduction of CO2 to zero, the remaining emissions from calcining that limestone are coming off in a pure stream or direct separation. So what this all means at scale is because it's more energy efficient and because we're starting from a fundamentally economic, scalable technology, we believe that this can be completely cost competitive with conventional cement production. So, the typical cost of cement, at least in the United States, is about $130 per ton. So using similar assumptions to recreate that price of 130 with our technology, we think as we scale from where we are today in the lab to our industrial demonstration, we can either be just as cheap or cheaper. And so kind of what is happening under the hood in this large scale is we're doing the same cement production chemistry. Instead of using heat, we're using electricity, a voltage. So just like you would charge a battery to move ions from one side of a cell to another, we're doing that with cement. So, step one, you have a calcination reaction. So we do that with our oxidation part of our cell. And then step two, you have a clinkerization reaction. So we make the clinker of the future. It is still a hydraulically active calcium silicate. We do it all in one single cell, all with less energy input. And so, the benefits of electrochemistry is that we can actually validate the technology even at a small scale. And from our testing of, smaller cubes, we've been able to demonstrate that at least according to the American ASTM standard, our strength development is exceeding the minimum requirements today. We think we can actually keep increasing that to be even a faster developing strength material while still keeping that calcium content much lower than conventional clinker. And we also, we're on track to make sure we meet all of the chemical requirements for that cement as well. And so, we're looking to actually rapidly scale this up. So we started at the milligram scale. The first experiments we did, we made calcium silicates that were so small you can only see them in an SEM. Luckily today we're making much more material at the gram scale. And even at that scale, we're able to move the process to a continuous flow cell before even scaling it up. And once we have completed that process, we will do a demonstration in our lab, about 1 ton per year. And we're targeting by 2028 to be doing a 10 kiloton per year industrial demonstration of that technology. And of course, beyond that to a full commercial scale. So we're really excited to be part of the GCCA. We kind of intentionally have engaged the industry, but despite being very early, because we want to make sure that this technology is actually on track to satisfy the demands of the cement industry. It's not our intention to be a cement company. I think there's a lot of really good cement companies in the world. It's our intention to work with them to create a technology that can decarbonize quickly and at scale. And so the first goal of the consortium was just to send our material to them to validate that it is kind of meeting the requirements, and then get their feedback on what we should do to modify our technology in order to make sure it is scaling in the right track. So we sent 20 grams of material to Bootsy, who agreed to test it. They did, despite it being a small amount of material, they actually were able to do a lot of tests. And very quickly, they were able to identify a couple of tweaks that, for us, we had no idea were kind of considerations that we might want to do, but for them were massive concerns that are easily modified. So even just in one iteration, we made a little bit of material, we said, hey, just take a look at it, and very quickly we got that feedback. Instead of spending months or years making a material that was just slightly off, we could very quickly go, okay, let's make sure we're changing our process and scaling it in the right direction. And the goal with that mentorship is actually to continue this iteration of the consortium. So as we continue to scale, make modifications of our process to adapt to their input, and continue to develop a complete replacement material. So I think that was really quick, but I'm sure there's a lot of questions, and I'm super happy to take them.
First question.
So if I understand the whole process, you're using electrochemistry to avoid the fossil fuel, and so CO2 reduction comes from the fossil fuel reduction. That's number one. The second is the CO2 which you generate from the process. Where does it go? Is it goes back into any other system? And third question is, what about drying? Because it's energy intensive.
Yeah. So there's three aspects to carbon reduction. So yeah, of course, not using fossil fuels, we can go to electricity. But at least with the electric grid in the United States today, the energy intensity of our process times carbon intensity of that is lower than the average carbon intensity of the cement industry for energy today. So we can decarbonize with electricity now, and of course, get that green. The second is we have less calcium in our final product. So we can still hit that compressive strength, with much lower calcium, maybe like half. So we can get a reduction in emissions there. And then third, if you want to take it to zero of direct emissions, we could capture that because the only thing coming off is CO2. So we're able to do a direct separation to get an off-taker to utilize. Yeah.
And do you have to dry the calcium silicate which comes out?
Yeah, so yeah, there is a solvent recovery loop. So the process is in a calcium conducting electrolyte, but it's a non-aqueous electrolyte. So it is much easier to dry. It does take energy, but we believe even considering that energy, the total net energy required of the whole process is still less than the conventional pre-calciner clinker cooling process.
Thank you.
Yeah.
Thank you. So far, have you used like natural limestones with the impurities or only pure reactants? And what could be the effect of using natural limestones with the impurities that we normally have?
Yeah, so yeah, we have focused mostly on kind of higher grade limestones, but we actually think our process would be fine to use impurities, especially if they're the same type of impurities you would get in the conventional production. So we actually even believe that there's a chance we could use a limestone that actually has a higher magnesium content because our process would be selective to calcium. And so you'd have to deal with what the waste magnesium is. So we'd have to deal with if there's a whole bunch of extra stuff we don't use, what do we do with that? But at least going into our material, it wouldn't affect that process.
Questions? We have no question online for time being. Yes, we have one.
So can we use low calcium mine tailing also for partial replacement in this electrochemical process? So that's really a step way further than Daniel.
Yeah, so yeah, we actually think that you could use a collection of different calcium inputs. We focused on limestone because that is the dominant input in the cement industry today. But if you had some easily distributed and cheap source of calcium to feed to the process, we believe that would work as well.
Still have time for one question. Online? No, no more questions. So thank you very much. And the fourth presentation, Neocrete. And same rule, you have 12 minutes.
Thank you. Hi, my name is Zarina, and I'm a CEO and a co-founder of Neocrete. We're a New Zealand-based company, and I'm here with my co-founder, Matt, Probably most of you have met him by now, and our technical lead, Michael. And firstly, thank you so much for this opportunity to be at the conference and learn firsthand from all the industry experts. We learned a lot about it, and I'll probably share some of the findings that we learned. And but we all agree, the first thing that we all agree on is cement is a great building material. The way we build, how fast we build, and even what our buildings look like, it's all predetermined by cement. And the whole construction industry is set up around what cement can do. So therefore, to disrupt cement means to disrupt the whole construction industry. And any solution to decarbonize cement can only be successful if it can match the performance of cement, can scale fast, and make economic sense. And that's what our technology addresses. Well, if we look at the typical cement manufacturing process, we learn that to turn raw materials into this amazing binder, they need to be highly processed. They're heated to extreme temperatures, and then further CO2 gets released as a byproduct of chemical reactions. So activation of the materials is where all the emissions come from. Neocrete came up with the more sophisticated way to activate the materials using chemistry and nanotechnology. Our nanoactivator is only added at 2 to 3% to raw materials, and it creates similar chemical reactions, but without the need for heat and this bulky, costly, and carbon-intensive production process. And we've further replaced our raw materials with pozzolans because they're low carbon, low cost, and they are largely available, abundant around the world. So we basically activate the low activity materials and turn them into a superior binder without further processing. And that binder, low cost and high performing binder, can be used as an SCM in concrete or can be used as a clinker substitution in cement. But one thing is to develop technology in the lab, and the other thing is to actually turn it into a useful solution for the industry. And we were listening to what the industry is talking about. And yesterday, I was asking the panel, what is one thing that you're all looking for? So how do you choose from those millions of decarbonizing technologies? And they say scalability, because cement is a truly global product and it needs to scale fast. And remember, our technology is only added at 2 to 3% by mass of cementitious materials or raw materials. Therefore, it means that the small-scale plant can service a large volume of materials. For example, in New Zealand, our pilot plant will be able at full capacity to serve up to 10% of cement market. And then the other thing that was discussed is the cost. And cement is an essential product, and we just can't afford to make it more costly, significantly more costly than it already is, especially outside of Europe and America. So we can't afford to triple or double the price of cement. And because we don't use heat and we don't use high processing energy, we can, even at moderate scales, we can be less costly than cement. And then lastly, performance. We don't want to compromise on performance in favor of carbon reduction, because concrete is the foundation of our homes. It's our critical infrastructure. And if anything, we actually want to make it stronger and more durable with all this weather, climate change events coming up more and more often. And our technology matches same one performance already at 50% substitution level, and we improve durability characteristics. For example, we significantly reduce water permeability and chloride penetration, making it more and more durable. And the carbon reduction is we're currently at 50% reduction, so replacing cement with our pozzolanic activated material. But we are working, and our long-term goal is completely replace the need for clinker. And the other thing about our technology is that we can further activate all emerging technologies, because we can activate cement and different cement-like technologies that you've just heard about. So we can help other technologies to also make it to the market. And because we were able to address those big challenges for the industry, we have already been selected for a number of flagship projects in New Zealand, like the expansion of our Parliament building and the National Repository. And we have proven our performance in a number of other buildings across New Zealand. And we're currently testing our technology with a number of customers inside and outside of New Zealand. And at a glance, you might think that those substitution levels are pretty, not that impressive for you. But remember, I was talking about the performance. So firstly, we perform or outperform SEM1 at those replacement levels. But also, we're using, for example, for Brunei, we're using highly inactive, not classified fly ash that was mixed with bottom ash. And without Neocrete, they were able to achieve 10% substitution level. With us, they can achieve 40% substitution level, and they further reduce overall cementitious material. And some of the other technology actually needed high early strengths because they were precast panels, and we were able to provide significant substitution levels and high early strengths. And, well, we all want to make a global impact. And global impact is impossible without global adoption. And that's why we're so happy to be in this room and being part of the Innovandi Challenge. And we actually work with 8, like our consortium consists of 8 global cement manufacturers representing around 30% of the global cement market. And they're sending us 6 different pozzolanic materials from around the world to see how we can activate them at 25% and 50% replacement levels. How are we going to test it? Well, we're testing them in mortar, in concrete, and we're testing the materials. And mortar and concrete will be testing fresh concrete properties as well as strength. And what to expect as results? We just started receiving the materials. We don't have the results from those specific pozzolans, but I'll show you some examples that we tested in Singapore. This is on the left-hand side, you can see 2 controls with SEM1, cement-based control, and 50% substitution level with the superplasticizers. And the green one is Neocrete at 50% replacement levels with slag, and Neocrete activator at 3.5%. You can see that the activation is so significant that at 50% substitution level, we outperform SEM1 control concrete, not just 50% replacement. And then the other one is natural pozzolans. Natural pozzolans, for perspective, are not used in New Zealand currently in construction because they're considered as low activity levels and not economic to be used. And we were able to provide 40% substitution levels and match the performance and outperform on day 28. What's next for us? Once we finalize the lab testing, we're hoping to get to scale trials and to prove our technology at scale with pilots with the consortium members. And the other thing that we notice here is that, before coming here, we hear all these huge names in the industry like Heidelberg and Titan and Cemex. And it's really easy to forget that behind all those big brand names, there are people. And here we can see that there are people who are very passionate about what they do. And we at Neocrete believe that technology doesn't change the world, people do. And people who can decarbonize the industry are here in Bangkok and here in this room. And we're really looking forward to working with you. Thank you.
So, questions? We have a set of questions online and then in the room.
Yeah. The one in the room, you can still ask your question after. So we go first online. How would you address the bulk handling and precise dosing of nanomaterial in continuous process cement production?
Yes, so is it about homogeneous mixing with, I'd imagine? Is it more about that?
I understand is really the dosing of the material.
Yes, because it's only at
when you will
percentage.
scale up. Yeah.
So we have an agent in our activator that actually makes it spreads across the mix much easier. And one of the parts that we'll be testing with this at scale is that premixing it as a clinker substitution rather than cement. So in concrete, it premixes really well and it gets activated by water as well. So then it mixes with the water. But in cement, they'll be interesting to see. But we have the agents that should address that.
Thank you. The next one online is, does the activator from Neocrete generate CO2? So what's the CO2 footprint of that activator?
So we're just finalizing our pilot plant in New Zealand, and we're hoping to produce our activator at very, very low, if not zero CO2 emissions. And the biggest part, because we don't use heat and we don't use a lot of energy, and we can probably have all our energy from solar panels And that way we're going to reduce our CO2 emissions. So the CO2 emissions are only going to be from transporting the materials, which is minimal, as we use mainly local materials.
Okay, and a related question, nano-additives are perceived to be health hazard in powder form.
Yeah.
How your process address this concern?
We do not have anything that is toxic to the environment or people in our activator. And the handling instructions are really like the same handling instructions that you'd use for cement. Because it's fine powder, the only health and safety hazard is like just breathing in fine powder, but there's nothing toxic in it.
Okay, you can actually watch the camera when you answer because you're not answering to me, you're answering to
sorry,
online.
sorry.
So I will go with the next one. Pozzolening material is not easily available everywhere. Is the sourcing and transport of pozzolanic material factored into the overall cost?
Yes, so we are looking at setting up plants and sourcing local materials and local pozzolans. So the less we can transport, the less CO2 there is, and the more we can reduce the cost. And yes, they're not available everywhere, but in New Zealand, natural pozzolans are available, industrial pozzolans are imported. But in different parts of the world, there'll be different pozzolanic materials, natural or industrial. And those parts, when there's no pozzolanic materials, we can potentially activate other types of materials that are already used as SCMs. And that's the beauty of chemistry. You can repurpose whatever reactions you're looking for, depending on the geography and depending on what the customers are already using. So we can tailor it.
There was one question in the room, there first, and then a second one, short one.
So the activator, is it a natural material or is it manufactured, number one? Number two, the powder form or liquid form. And the third is the Singapore example which you were talking. So is it a steel slag, iron slag, or some other slag?
Yeah,
which
GGB,
industry
yes.
it is?
Yeah, steel slag.
Okay.
It's imported from China to Singapore.
Is it blast furnace or a steel?
Yes, yes.
Blast furnace.
Blast
Okay.
furnace slag. Okay. And answering manufacture. So we use mainly minerals, natural minerals for production of our activator, and we include a manufactured superplasticizer that we also modify, which actually helps disperse our activator at small percentages, and it comes in a powder form. And in the regions where we can't find those natural minerals for our activator, we can manufacture those and synthesize those, or ask the external parties to synthesize those.
And the very last question?
You outlined two steps in your process, the natural pozzolan and the activator. Can those two processes be decoupled and your proprietary activator be used with any other material that you find in quarries or within cement plants?
Yes, we would have to test it, but the question is, can they be pre-mixed together, or can we just use...
Can we use your product without any pozzolans?
Yes, absolutely, and it activates cement. You can put it cement and replace it with aggregates like sand, inactive fillers, and still achieve cement reductions, but limited, maybe 30% max from our trials.
Thank you very much. I think it's time, sorry for that,
no,
but you have 12 minutes and not more. Thank you. Then we take this opportunity to present to not the startups, but where we stand regarding two consortia that were launched in the first Open Challenge. This one was dedicated to carbon capture. And then I would like now to have the mentor, Daniel from Argos, to present where we stand on the first one, and I will present on the second one.
Okay. So I will be presenting on behalf of Carbon Biocapture. So they sent the slides, so I will be presenting in their behalf, and I will be doing if I am part of that company. So let's go. Okay, the green one. So this is a technology to convert flue gases or CO2 emission into biomass, and is funded by Andrea Irarrázaval from Chile. So how the technology works? So you build a photobioreactor farm, and those photobioreactors with microalgae inside the photobioreactors are fed with the flue gases. And the microalgae, they do what they know to do by nature, is to synthesize that CO2 and convert that CO2 into biomass. So that's what the technology does. And as a byproduct, you have this biomass that then you can convert into something else. Okay, the company has patented that technology in those countries, and microalgae can have much CO2 productivity or better CO2 capture productivity than trees. Okay, let's continue. Okay, what are the environmental benefits? This technology can capture up to 96% of the CO2, also can capture the NOx, the SOx. The byproduct is the biomass, but as well oxygen. It can be used to recover degraded soils. It has some social benefits related to the jobs that can be created, enhance the relationship with the authorities, and also some financial benefits as the CO2 can be converted into a byproduct that can be commercialized. Okay, let's continue. So these are some examples of the byproducts that can be created. So the company have done some tests converting that biomass into biofertilizers. So here are some of the examples. Also, the technology have developed some sensors that can be added to the panels in order to continuously measure the CO2 that is captured by the panels and to measure the conditions inside the photobioreactors like pH and so on in order to determine the right conditions to grow the algae. Okay, so as Adelio explained, during the first Open Challenge, this company was selected and we create a consortium with Argos, CEMEX, CRH, and Holcim, and we define some objectives for that project. And the idea is to prove the CO2 productivity that we can achieve, to design, build, and operate a pilot plant, and to transform real flue gases into that biomass. So this is the main objective of the project is to confirm that we can capture 840 metric tons of CO2 per hectare per year. And this project will encompass, during the project, the company is going to make 4 feasibility studies for each member. So each member has sent a sample of algae that were, let's say, harvested in the plants for the members, and the company is growing those algae in a lab, and then they are going to be put into the photobioreactor. So each company will have an array of photobioreactors to test their own microalgae species. So the project has already complete the tie-in to the main chimney, to the main stack. They are in the process of building the photobioreactor farm, and we hope that in the next 2 months, the plant will be commissioning and the testing of the CO2 productivity could begin. The idea is the project that will run for a year, because in this type of biological processes, seasons are very important. So we want to measure the productivity during summer as well as during winter in order to have a medium productivity over the whole year. Okay, then as with all other startups, the idea of this initial project is to create the links, and then each company could decide on deploy it or make larger scale projects at their facilities. And the idea of the company is for sure to support and achieve our decarbonization goals and objectives. So this is in the videos you can see some of the trials they are doing in their labs. Okay, that's it. Thank you very much.
Thank you. Questions?
Yeah, is the emissions or the gases are directly feed to the algae, or it goes through some filtration or purification process?
No, no filtration. They are directly feed into the photobioreactors.
At a high temperature?
Yes, as the pipe is around 40 meters, they cool down a little bit. But normally, that cool down is enough. So you don't need to make any treatment of the flue gases.
Okay.
No.
Capturing plant?
No, I will prefer to defer that question to them. Yeah.
Thank you.
Is the idea that the photobioreactor be co-located at the cement plants, or would this process be better suited for something like carbon captured from the flue, transported to an alternate location to then be transformed through this process?
I think both could work. So what we have done is to locate the photobioreactors in the cement plant. But given a scheme of a CO2 hub, and there is enough area close to that CO2 hub, why not?
Okay. A follow-up question to that is, assuming a typical cement plant, how large of a space would this setup require?
But, sorry, a CO2 hub, there you have already the CO2 treated and pure, let's say at 98%. So with this technology, you don't need to do the capturing of the CO2. So you can use the flue gas directly. So a better question and better answer will be, ideally, you should use this technology in the cement plant. And how much you need land? So can you capture 100% of the CO2 emission of the cement plant? Maybe not. If the productivity is increased a lot, and then you begin to do genetical modification of the algae, maybe you can achieve a productivity that allows you to use the land that you have in close to the cement plant. But if not, it's maybe better to think on a solution to capture, to transform some percentage of the CO2 that you produce at the cement plant, and the benefit is that you can make a business out of it by commercializing the biomass or transforming the biomass into something else.
I have another question there.
Daniel, what can you tell us regarding the water consumption on this?
No, I don't have I don't have the exact value, but the only water that you lose is the water that is evaporated. So you can't reuse. You normally can reuse the water, but I don't have a figure of water consumption and recyclability.
Another question there?
Can that biomass, algae biomass, which is generated, be again used as a fuel for the cement?
Yes, why not? Yes. Yes. You have maybe to dry it.
Dry,
Yeah.
yes.
But this is one of the options we have thinking. Yeah.
Good. So thank you very much, Daniel. Just a comment, if I may. That's a fantastic example of how the way GCCA can collaborate, the members can collaborate together in order to share the cost for this implementation, etc. So obviously, everyone can do it by itself, but just collaborating, and sharing the information is by far accelerating the growth of the startup. So we hope the same for the different 4 startups that presented before to go to that level. There is another example, Nuada, that we would like to highlight, not in details, because unfortunately they could not come, but this is the second consortium which is almost commissioning the first pilot plant in Italy for Buzzi. So Nuada, that's a technology for carbon capture. This is very much based on metal organic frameworks. And this technology has been hosted and piloted and promoted by 7 GCCA members. So Cementir Holding, Heidelberg Materials, Buzzi, Unisem, Cementos Argos, Holcim, Siam Cement, and Cementos Molins. They are not here, unfortunately, today, so we will not explain in details the technology, but just be aware that this second consortium is progressing well, and the pilot commissioning is ongoing. So there will be no presentation, as I said. We move now to the next Q&A sessions. We still have a bit of time, so if you have any question related to the 4 presentations that were done just before, not on the biocapture, carbon biocapture, but on the 4 we still have time. So if you have any burning question, if you have whatever, a comment to make, we still have a bit of time. Online or in the room. So there is the first question.
Okay. I think my question is to Queen Cement. This might sound...
So Queen's Carbon.
Yeah, Queen's Carbon, sorry.
Okay. Otherwise you have Chement, but yeah, you have to select one or the other.
I'm trying to understand the process a little bit. And forgive me, I'm a cement person by trade, right? So what's been drilled in my head is the phase diagram and how you make clinker. I'd love to understand what happens and what your what your microscopy looks like. What does that whole process look like in that reactor?
Yeah, we'll give some clues and some insights of what's happening. There's this whole world of hydrothermal chemistry where you use water or solvents to dissolve something and then you reprecipitate it, right? And then there's this whole opposite world at high temperature zones where you have a solid state reaction, similar to what happens in a kiln, right? You heat things up, they react, and then you have partial melts and clinker that forms. In our case, we're kind of a hybrid between those 2 worlds, where you have kind of water-activated chemical reactions, where we're actually never sintering anything. So we don't have a grinding step at the end because there's no clinker that's actually formed. It's a powder that's formed. So throughout the process, you put in your powdered raw meal, you have a water-enabled chemical reaction that occurs. The CO2 exits the stream. Inside of the materials transform into a calcium silicate, and you separate the water from the CO2, and now you have a pure CO2 co-product. What we'd see under? So because we're never partially melting or partially fusing or sintering, it's going to look a little bit different. We're not grinding to a final Blaine number. There's nothing to grind. There's no nodule that comes out of the reactor, right? We might do a mild deagglomeration step, but that's it. So it's going to look a little bit different, and our intent is to work with the industry to make sure that's widely accepted. Our preliminary performance indicates that it should be, but further feedback as we get into durability studies and et cetera, we'll speak to that.
Just real quick, so I'm really interested in trying to understand what it does to the overall water demand if you're not grinding and the overall clinker structure, the structure of it. Because water demand not only is strength, water demand and how that all reacts is very important to the product as well. So if you're not grinding it, you're mixing it, what's the sizing coming out of that reactor?
Yeah, and maybe I spoke too soon. So if you could imagine if we're on site at a cement plant and we're integrating into that finish milling, that finish grinding step, you effectively are co-milling, co-mixing inside of that grinding step. So the homogenization of our material with clinker is done in a one pot system, right? So we're injecting our material back into the stream at that finish milling step. So that's where you have a very good homogenization. To the water demand question, every emerging SCM has to answer this question, and so do we. And so we're working our way to get to parity with PLC. That's where we're working towards now.
I have a question there and another there.
Yeah. My question is to the team from Neocrete.
Neocrete.
Yeah. So now the material, is it more easy to be used in ready-mix concrete as compared to cement? First question. Second, today in case of ready-mix concrete, there is a limitation of replacing SCM, say for example, 35% fly ash and maybe around 65-75% of ground slag. So there are two considerations. One is the strength part, high early strength, and another is the durability consideration. So does your material help to increase the threshold from 35%, say 55% replacement of fly ash, giving a better early strength? And what about the durability? And similarly with the GGBS, that is the ground slag, whether we can further increase to get a better strength and a durability consideration.
Thank you. So there are limitations currently in how much pozzolanic material we can use in concrete from the building codes in different countries. In Europe, I think it's 55% already, and in the US, it's 40%. So we can already pretty much max out, so reach those limits with different types of pozzolans. And your question was, is it easier to edit at concrete stage or cement blending stage? To be honest, we only tested it so far at concrete stage because it's easier for us to work with ready-mix supplies without disrupting the whole cement manufacturing. So as part of this association and challenge, we are hoping to test it in the real cement manufacturing plant and see, is this easier as a cement manufacturing plant? We believe that it's going to be more active, so we would need to add even less of our activator the earlier you add it at the process. So if you added at cement process, we probably would need 1.5% of our activator. At concrete plant, it's going to be 3%, let's say. But we need to test it. And the other question about high early strengths and durability, yes, we increase strengths to match the strengths of cement on day one and every age of strength setting. So yes, with fly ash and with slag, that's one of our key advantages, especially for precast concrete that requires high early strength. So therefore, they actually don't have options at the moment to have significant substitution levels because of high early strengths, and it adds cost to them because they can't demold the next days, and it means they can produce less and less. In terms of durability, we actually enhance durability because the other properties that I didn't have time to talk about is that it's impermeable to water. It's impermeable to seawater. That means that it doesn't go inside the structure of concrete, doesn't go to the reinforcement. So it protects the steel reinforcement much better than clinker-based cement. And therefore, we are also better prepared for all the climate change and different types of like flooding and all those events much better. So it's a sustainable product from all sorts of angles, not just from one, not just from CO2 reduction.
What is the percentage increase in high early strength?
Well, the thing is, what our testing does is that we get to the same strengths as control And then if it's higher than controlled, then we reduce cement further and further. So with natural pozzolans, we got to 40% replacement level and we match the same strength. So if you don't replace cement and just add it to it, it's 270%. If we don't replace cement and just add our activator at 3%, it's significantly higher than normal concrete. So what it allows us to do is to replace cement to just match the specifications of that grade of concrete, because we don't want to overachieve either.
I have one question there and one there.
My question is for Queen Cement, Queen Carbon.
We'll rebrand soon.
No. So, where is the question actually? I want to ask about the water consumption in your process. So, do you have a figure of how many liters of water do you need per ton of product?
We have a good understanding of what it is now, and what we're working, the water amount that we're using in the laboratory now supports our 2 to 3 gigajoule per ton number of the overall process. So we're not consuming any water. It's basically a steam pressure. There's no water that's consumed. It's fully recycled, fully closed loop. So it's, and as part of our process engineering, we're minimizing that as much as possible.
Could you help us? Could you explain us a little more on that? So it is steam based. You put it in the pot. Then, how is the water coming back? How is it recycled?
As soon as on the outlet, you take out your solid materials, and you also want to retrieve. If you didn't use the CO2, you want to retrieve the CO2. You have to condense the water, right? Once you condense the water, it goes back into the system.
Thank you.
Yeah.
Clear.
And one question here.
My question is from Queens, Neocrete. So we understood your activator is used along with pozzolanic material or slag. What if we will not use these pozzolanic material or slag? Directly reducing cement consumption. For example, for achieving some specific strength, we are using 300 kilogram of cement in 1 meter cube concrete. It to reduce cement consumption to 200 kilogram.
Yeah, so the question is, can we use the activator without the pozzolanic material and just reduce cement content?
Exactly.
Yeah. So reduce total cementitious content is that right?
Yes.
With our trials, we were able to do that in New Zealand by 30% with just the activator, because it activates cement as well, and therefore you reduce cement content and overall cementitious material. And in places where there's no access to any other SCMs, that's the solution. Or for plants, ready-mix plants that don't have silos, specifically for additional materials, that's another solution. It's just going to be limited to like 30% maximum reduction, and replace it with inactive filler like sand. In New Zealand, unfortunately, there's also not enough sand, so it's kind of we're balancing out the the pozzolanic material and sand and virgin sand.
Okay, thank you.
Good. Okay, so the very, very last one. Okay, the last two ones. And then we stop, otherwise...
Short question. Your trials were with OPC cement, from what I understood, right? Mm-hmm. Have you done any trials with blended cements?
No.
Or not yet?
No, not yet,
Thank you.
but we'd love to. Yeah.
Thank you. Thank you.
And then last one.
And it's just to
very,
clarify,
very
we only
one.
have SEM1 in New Zealand. Yeah, so no blends. Yeah.
Yes, the mic.
So this is a question for EnviCore. The process that I was explained, it's an SCM that gets mixed with clinker or in cement. Can you mix your SCM with what we call in the US type 1S or slag cement to further increase your reductions?
Yeah, no,
and
absolutely.
to what capacity could that be done?
Right now, we haven't tested like to what extent we can mix with other blended cement with other SCMs. But that's definitely one of the work that we are prioritizing and focusing on is to evaluate like SCMs such as fly ash, GGBFS, and a bunch of even our own SCM coming from different operations, different material stream, and blend it together and basically just measure the strength. but it totally depends on what sort of material we have availability in that particular location where we are producing the SCM in the first place. So everything goes back to the logistics and supply chain of the available SCMs and what we can produce from like different sources.
And from a reactivity perspective, can these materials be pre-blended? Because there's typically silo space constraints within ready-mix pipelines.
Absolutely, yeah. Thanks.
So thanks for the question. So now I will leave the floor to Claude, but just many thanks for the startups for coming, and to mention as well that some venture capitals were connected online. So that's we wish you all the best for this, and obviously you will be connected with these people. So now Claude for the conclusions.
Thank you, and I won't be long. First, I want to thank you, Edelio, for having moderated this day, but also for having been one of our leading member in developing this challenge, because there is really a lot of work behind this. I think that yesterday we were explaining at the GCCA conference, we are now at 262 startups that have been assessed by the GCCA members. I think it's a big thank you as well to all the company experts that put a lot of dedication to quickly assess the startup. We are trying to share the learning. I think we are all learning, the startup are learning, but our industry is learning as well. I also want to highlight that here you saw the 4 startups for that challenge that made it to consortium. Our rule is that to make it to a consortium that is managed by the GCCA, we need at least 3 GCCA members interested. But we know that there are startups that continue to work with 1 or 2 members. So you only see here the top of the iceberg. And we also have many startups that were invited to pitch to our members that are asking letters of support, that they were indeed invited to pitch, and I'm happy to provide those letters. And this helps also startup to get access to funding or to more support. So I think it's really important also to understand that we actually do more than just those consortium with our Innovandi Open Challenge. And then finally, we have also created an entrepreneur network. And that's another forum where we provide mentorship to startup. This is growing slowly, but surely. And also it's a bilateral relation we are having. So we have conversation with the startups and they are part of the discussion with us. Now there is one person that was not on stage today, and it's Devika. And I would like Devika to come here with me, because this would not happen without Devika Vatal, who works from Mumbai. I think sometimes in life you need a bit of chance to meet people. It's now 3 years I work with Devika. It's our 3rd challenge, and I think it's really fantastic. And if everyone agrees, I would really like us to do a big congratulations to Devika. And then what's next? And it's still with Devika, because she also happens to know really a lot about CCUS. I got a question online when we would launch our 2024 challenge. This has been launched, and we're actually quite far already in the process, because we have already selected the startup that were invited to pitch, and we actually already had the startup pitching, and we actually already have an idea how we are going to move forward. But we had really a high level of application in the 2024 challenge, and I think that soon we will discuss what will be the 2025 one. But so clearly we are going to continue. So that will be my last slide. We have 2 more things to do today. That I have been asked to invite everyone in this room to come here in front, so that we can take a group picture. And then I will ask all startups to stay so that we can have a startup picture. But so everyone come with me. And as you are all walking here, I also want to thank our members and not only Adelio, but everyone who is contributing and helping us with the startup. Thank you, everyone, and thank you to all our guests online. We will share the recording of this event, and we will make sure that the unanswered questions are answered. Thank you.